All right, this is a quick follow-up to my previous video about non-rigid transformations. And now that we've put a whole bunch of transformations together, I wanted to just briefly discuss how to actually graph a transformed function, because there's a lot going on here. There's all these transformations, and it might be a little overwhelming to try to graph. Although we could sit there and we could try plugging in a whole bunch of points, that's not always the most time-efficient way to come up with the transformed function compared to its parent function. So I wanted to give you my streamlined approach for this. This may not be the only way, but this is the one that I found works the most for me. So what I start by doing is I want to start by, let me actually change the color of this. Let me put this as, let's go blue. All right. And in blue, I'm going to write the parent function point. So I'm just going to first create a table of values for my parent function. Since this is a cubic function, I think it's easiest to just start with -2, -1, 0, 1, and 2. These are the x values. Now, if I evaluate my function at each of these inputs, I'm going to get -8. I'm going to get -1, 0, +1, and +8. Okay, so I could graph that. So -2, -8, 1, 2, 3, 4, 5, 6, 7, 8. -2, -1, 1, -1, 0, 1, and +2, and then where's +8? Right up here. Okay, so this graph is going to look something like this. Not a fantastic function, but you get the idea. Okay, so something like this. There's my cubic. Okay, obviously I could have done that a little better, but it's just a sketch. All right, so now let's take care of what's happening to our argument first. So 3x plus 1. I'm going to take care of what's happening to our argument first. In my previous video, I said, in order to figure out where these x's go, let me actually change the color of this. To figure out where these x's go, I want to set my argument. So 3x plus 1, I'm going to set it equal to the original input. So in the first case, I'm going to set it equal to -2. And I'm going to solve for x. I'm going to see where does this x go now. If I apply the inverse operations, because again, I'm applying these transformations before I plug it into the function. So I've got to do the inverse to get back to my original spot. So what do I need to do to x to get back to -2? So I'm going to first subtract -1 from both sides. Okay, and then x is equal to -1. So this -2 now is going to move to -1. That's where its transformation goes. So we're going to rinse and repeat this process of setting the argument equal to my x value. So my x value here is now -1. 3x now is equal to -2. X is equal to -2/3. And that's what goes here. All right, and let's just continue rinse and repeat here. So if 3x plus 1 is equal to 0, x then is equal to -1/3, which is what I'm going to write here. Just make a little space. Set this equal to 1 now. When x is equal to 3x plus 1 is equal to +1, x goes to 0. And when 3x plus 1 is equal to 2, then that would be x is equal to 1/3. Now, pause and make sure that this makes sense to you. Think about this for a second. Previously, we said that this was going to be a horizontal shrink by 3, and then a horizontal shift to the left by 1/3 of a unit, right? So if take, for example, something like this input, 1. If I shrink it by 3, okay, if I shrink 1 by 3, now that 1 goes to 1/3. 1 goes to 1/3. And then if I horizontally shift that to the left 1/3 unit, 1/3 goes to 0, which is what I have here. Now, if I had done that the other way, if I had said this was a horizontal shift to the left 1 unit, and then a horizontal shrink by 3, that also works as well. If 1 goes to 0, because you're shifting to the left 1 unit, and then shrinking it by 3, well, 0 times 1/3 is still going to be 0. Or 1/3 of 0 is still 0, I should say, is probably a better way of saying that. So I still end up in the same spot. So these are now my new transformed horizontal values. Now, what about for the y's or the f of x's? Well, this is actually more straightforward. We don't need to set our y values equal to our argument. We can just apply the transformation directly. So what's going on here? We're going to multiply by -2, and then we're going to add 4. Okay? So -8, so let's do this. -8 times -2, and then add 4. That's just going to give me 16 plus 4, that's 20. So this -8 now moves to +20. So we did -8, the original output for our parent function. We vertically stretched it by 2, so we went from -8 to -16, then reflected it, which was +16, and then we vertically shifted it up 4, which gets us at 20. Same deal, we're going to rinse and repeat that for -1. So -1 times -2, which is +2 plus 4, that goes to 6. And again, work through the transformations in your head. If I take -1 and I stretch it by 2, so -1 goes to -2, reflect it over the x-axis, so -2 goes to +2, and then shift it up 4. Now we're at +6. So you can run through them pretty quickly now. 0 times -2 is 0, plus 4 is 4. 1 times -2 is -2 plus 4 is +2. 8 times -2 is -16 plus 4 is -12. You can check my math. Hopefully I did all those correct. Now, what are the values that we're going to graph? We are going to graph now, let me put this in a different color. G of x are these values here, our transformed values. So G of x's table, let me actually just make some space here, is just going to be this. -1 results in 20. -2/3 results in 6. -1/3 goes to 4. 0 goes to 2. 1/3 goes to -12. And a lot of these points I can't really graph very well because I've done some shrinking and translating and reflecting. This is going to be a little bit hard to see, but you're going to get a point way down here. -2/3 is going to go to up there, I should say. -2/3 is going to go to 6. 1, 2, 3, 4, 5, 6. -1/3 is going to go to 4. 0 gives me 2. 1/3 gives me -12, which is down here. So your graph is going to look something like this. It's really hard to see. I probably should have rescaled my axes so we can see the reflections and all the transformations happening there. So hopefully that helps kind of give you a streamlined approach for how to graph a transformed function.